Welcome to the course on Introduction to Electrical Engineering. So, we will discuss on in lecture 12 today on single phase AC circuit part 3, and to start with outline of this today presentation. After introduction of topic, we will talk about single phase AC circuit, the power in AC circuit with the active, reactive and apparent power and power tangle concept. Then we will discuss about power factor, then we will talk of active, reactive component of current, and we will talk about some exercise and numerical analysis. So, coming to like typically we can say we will talk about active, reactive and apparent powers. So, with the example here, real power flow without reactive support, from generator it flows to the load, but if you have a real power with reactive power support, from generator you provide the reactive support, then it flows to the load. So, it is just like given a concept that reactive power is measured in VAR is required to maintain the voltage to deliver active power via transmission line. So, here we have a concept of 3 power: active power which is really consume and does the work, and reactive power which is responsible for, of course, typically it goes to the typical load or circuit and come back in another half cycle, and then of course, because whole power circulate. So, typically we will calculate from both the power which are at 90 degree, we call power tangle. So, we will discuss about the apparent power. Of course, different equipment are rated on different powers. The typical example is motor, and your heating load we rate in terms of watt, kilowatt or horsepower or megawatt, and reactive power of course, we call it VR, MVR or kVR, and apparent power of course, we talk about VA, kVA or MVA. So, these are 3 different powers. Of course, the generator and transformers, they are always rated in terms of kVA, MVA, and your typically your reactive power elements like inductor and capacitors, they always rated in VAR like. So, now we have we define the power factor here. Typically we say it is a 100 kVR. If we have a 100 kVR, 100 kilowatt consumed by the load. So, we say total kVA will be of course, square root of both 100 square plus 100 square. So, that will become root 2 into 100, that will become your 142, and power factor will be your 0.7, because power factor is decided by your active power divided by apparent power. So, that will be like 100 upon 142, that will be 0.7. So, we can say again, if you have a reactive power, reduced reactive power here 33 kVR, but active power remains the same 100, then your kVA is 100.05 and power factor goes to 0.95. And if you have a 0 kVR and 100 kilowatt load, then you have a 100 kVA, kVA and kilowatt are both same and power factor is unity. So, with this example, you can say power factor depict the distribution of real power and reactive power within the apparent power. But you can understand if the reactive power absorbed by the load is less. So, you will be having certainly the less current as well as the less current will be flowing through the distribution network, especially in the transformer as well as in your feeder like of the distribution. So, that is of course, one of the major is you can say issue or the problem in AC network, that you have to even typically have a reactive power also to flow through the these circuit elements like transformer, transmission line as well as. But however, this reactive power of course, can be generated locally with the help of reactive elements. Like if you have a inductive reactance, then you can put the capacitor locally there to compensate it. So, that from the feeder or from the transformer you draw only active power. Similarly, if you have a capacitive load, then it needs the reactive power of capacitive nature. So, you can meet from the reactor or inductive reactor to put across the load, and then you can fulfill the reactive requirement of the load locally. So, that it does not draw from the AC line, and the losses in AC line current as well as the losses in the distribution transformer or the typically your feeder are reduced like. So, that we call it like of course, power factor improvement. So, you can see here we have analog power factor meter, nowadays we have a digital meter also, and normally we say the passive power factor correction through capacitor bank with the inductive load like motor. As you know, we normally use the lot of AC motors like induction motor, we draw lagging current or reactive current or inductive current. So, we place the capacitor here in parallel to that load, which really meets the local requirement of reactive power, and you do not draw this reactive power from the line. And this has been sometime the enforcement on the industry to improve their power factor by putting such kind of capacitive panel, as you can see in the diagram. However, this capacitor you can connect in delta and star according to the your typically the connection or the level of the voltage which you are going to apply in the circuit like so these capacitors are put in shunt or in parallel across the load at the same point where you are connecting these loads like also. Well, we can say here now we talk about here power triangle. So, we have a two kind of load like inductive load. So, voltage current is lagging by typically a phase angle phi, in an inductive circuit, and in capacitive circuit the current is leading by the angle phi from the voltage. And this, if we talk about power, of course, x axis we put kilowatt, y axis we put kVAr, and typically phasor sum of these two we call it kVA, and of course, the angle between this called phasor angle called phi, and we define the power factor equal to actual power, that is your kilowatt real power divided by apparent power, or we say that is P power factor equal to cos phi if your current and voltage both are sinusoidal in nature, and that defines your really a power triangle. So, we have a real power on x axis that represented by P, it can be it is equal to S equal to cos phi, and real reactive power we say y axis. So, we call it this as a Q, and that is will be calculated as sin phi, where S is the apparent power, and of course, here it is in kilowatt, that is in kVAr, and this is on kilowatt, or of course, it can be like watt, VAR and VA, or it can be like a megawatt or MVAr or MVA. So, this we call it the power triangle in, of course, in case of your AC circuit like. So, now coming to active and reactive power component of the circuit, here you can have a 4 resistive loads, the current is in phase with the voltage, and the power can be seen in yellow, that average power is always positive, because you never go to negative. So, voltage and current both are in phase. When you multiplied, of course, power remain positive only, but of course, you have a fixed power, that is average power and pulsating power. And when you have a like a typically partial reactive load, current is either leading or lagging, as you can see here in that case. If you take a typically as a here the voltage as a red line. So, you have a current which is inductive current lagging, and now you will see the power is changing from positive to negative. Then voltage and current both are positive, you have a positive power, but when their sign is opposite, like you have here voltage negative, but current positive. So, power is negative. Similarly, when typically both go to the both goes to the negative, then power again positive. So, you will see that there is a power which is positive, but there is a power which is also negative. It means that power get, you can call it go on exchanging with the load and with the network, and this circulating power or exchange power which get stored in 1/2 cycle and return back to the source, we call it this as a reactive power. And of course, you can see average of this your yellow is the your typically the your active power. So, we can say of course, you may have a many kind of situation that the in nonlinear load the current waveform is highly distorted, and power factor need to be considered leading or lagging, depends on fundamental current and plus harmonic VAR. So, you do not consume here only the reactive power, but you all and real power, but you have a harmonics power also, because that will be also drawn by the load, and this causes the effect two major effect. One is that because the RMS current will increase because of harmonics, not only because of reactive power. Apart from this, that will increase the losses in the distribution system. Moreover, it will distort the voltage at the point of common coupling, which affects the even other load which draws sinusoidal current, because there are many load which really are sensitive to these harmonics. Like of course, resistive load may not be sensitive, but of course, inductive or capacitive load will be more sensitive. Typically, like a capacitive load will drop probably for higher order harmonics, it will draw not the proportional current, but much higher current. So, the you can call it, that is the reason we call it like this as a non-linear load. We cannot say that the current will be same shape as the voltage, in this case, because there are non-linear element like typically diodes and many such elements are there as a part of the load, and that practically happening in nowadays in many of the load, like your computer load, like LED lighting load. You have plenty of load of such nature in your present day distribution system like. So, now we define like a instantaneous power. The instantaneous power we say product of the instantaneous voltage across the device and instantaneous current through it. The passive sign convention is assumed. So, P t equal to V t into I t, and that P t V t I t equal to I square R, and we can say that it is typically V square upon R for resistive circuit, and P t equal to V t I t, that is for inductive load, it is L d by d t into I, that is your V t into 1 upon L integration of V t, and this we call it for inductive load, and this typically this power instantaneous power will be typically average of this will be 0, but you will be having circulating the reactive power for 1/2 cycle. The load inductor will absorb the energy, another half it will release the energy back to the source like. So, we can say here for typically for capacitive network also we can say P t equal to V t I t and V into C dV upon dt, that will be I 1 upon C minus into T I t into dt. So, here also you will find the 1/2 cycle the capacitor will store energy, another half cycle it will release the energy back to the source. So, this energy will back through will of course circulate the current in the network into the transformer as well as your feeder, but you will not consume any active power like for these capacitive and inductive element like. So, now let us come to the power to the sinusoidal excitation. So, let us change the voltage source in the circuit to sinusoidal source V m sin cos omega t, where phi is the negative for inductive circuit. You have RL circuit and you are having AC voltage source with you can say V 0 into u t, where u t can be like a typically your cos omega t. So, we can say I t will be I m cos omega t plus phi. So, where I m is V m upon under root r square plus omega L square L square, and phi is your minus tan inverse omega L upon r. So, instantaneous power delivered to the entire circuit in the sinusoidal steady state, therefore, P equal to V t into I t, and that is V m I m cos omega t plus phi into cos omega t, and this by using the trigonometric identity for the product of two cosine function, then we can say P t equal to V m I m by 2 cos omega 2 omega t plus phi plus cos phi, and here you can write this two term equal to V m upon 2 V m I m by 2 into cos phi and plus V m I m by 2 into cos 2 pi 2 omega t plus phi. So, here first term not a function of time. So, it is a constant, it is just like a steady constant power, and in second term the cyclic variation at twice the applied frequency. So, that is a kind of pulsating power. And so, since the term in a cosine wave and sine wave and cosine wave has average value which is equal to 0. So, we can say average power consumed by this RL network will be equal to half V m I m cos phi. So, we can say average power in the sinusoidal steady state more generalized case with the voltage angle phi theta and current angle phi. So, we can say where V is equal to V m cos omega t plus theta and current is I equal to I m cos omega t plus phi. So, we can take instantaneous power P equal to V m I m cos omega t plus phi theta plus into cos omega t plus phi, and of course, product of two cosine function as 1/2 of the sum of the cosine and difference between the cosine and sine. So, this becomes equal to half V m I m cos theta minus phi plus half V m I m cos 2 omega t plus theta plus phi. So, the power function has a period of half t and cosine and sine wave. So, that the average value of the either of a period is 0. By inspection the average value of the second term is 0 over the period of t or a half t, and now we can say the typically average power is P equal to half V m I m cos theta minus phi, and the average absorbed by power by an ideal resistor is P equal to half V m I m cos theta minus phi. So, for pure resistive load theta equal to phi. So, hence the PR will be half V m I m into cos 0, that is half V m I m, or P r equal to half I m square r, or P r equal to V m square upon 2 r. So, the average power absorbed by a reactive element, we can say average power delivered by any device which is pure reactive contains no resistance must be 0, and this is the direct result of a 90° phase difference between which must exist between voltage and current. So, cos phi minus theta minus phi is equal to cos plus minus 90°, and that is equal to 0. So, P x equal to 0. So, average power delivered to any network composed entirely of ideal inductance or capacitance is 0. So, instantaneous power is 0 only at a specific instant. So, thus the power flows into the network for a part of the cycle and out of the network during another portion of the cycle with no power loss. So, the effective value of a sinusoidal waveform. So, the most important special case is that of the sinusoidal waveform. So, let us consider the sinusoidal waveform I equal to I m cos omega t plus phi, which have a period t equal to 2 pi upon omega. So, we can say substituting in. So, we call it I effective, that is RMS current under root 1 upon t 0 to t I m square dt. and then we can say I effective equal to under root 1 upon t 0 to t I m square cos square omega t plus phi dt, or we say I m under root omega upon 2 pi 0 to pi 2 pi upon omega in bracket half plus half cos 2 omega t plus 2 phi dt, and that finally becomes equal to I m by root 2. So, that term second term will become 0. So, use the RMS value to compute average power. The average power delivered to R ohm resistors by sinusoidal current will be P equal to half I m square R, and we can call it I effective I m upon root 2 in case of sinusoidal excitation. So, average power may be written as P equal to I effective R, and that is P equal to V effective square upon R. So, other power expression may also be written in terms of effective value, that is P equal to V effective I effective cos theta minus phi. So, now we can define the power factor. The ratio of real power, real or average power to the apparent power is called power factor and symbolized P f, and the power factor or P f average power divided by apparent power, and we write P equal to equal to P upon V effective I effective. So, if sinusoidal case, the power factor is simply cos phi minus cos theta minus phi, where phi minus theta minus phi is the angle between which the voltage leads the current, and this relation is the reason why the angle theta minus phi is often referred as a power factor angle. So, the voltage and current are in phase. So, theta minus phi is 0 and power factor is unity like in resistive load, and apparent power and the average power are to be equal, and at unity power factor may also be achieved by load containing both inductance and capacitance. So, if the element values and the operating frequency are carefully selected to provide the input impedance having a 0 phase angle X L equal to X C. So, this we call it resonance phenomena, and the pure reactive load only connecting no resistance. So, phase difference between the voltage and current of either plus or minus 90 degree, and the power factor is therefore 0. So, the power factor, the terms leading or lagging refer to the phase angle of current with respect to the voltage, and thus the inductive load will have a lagging power factor and capacitive load have a leading power factor. The magnitude of complex power is simply the apparent power, and the real part is the average power, and imaginary part is we call it new quantity term as a reactive power, and describe the rate of energy transfer in and out of reactive load component, that is inductors or capacitor. So, the average power absorbed by the two terminal network is therefore P equal to V effective I effective cos theta minus phi, and complex nomenclature is next introduced by making use of Euler's relation. So, we call it like a P equal to V effective I effective real part of e to power minus j theta minus phi, or we say P equal to real part of V effective e to power j theta I effective e to power minus j phi, and we say the average power absorbed by the two typically. So, that equal to that is the phasor current is I effective equal to I effective e to power j pi. Well, therefore, we must make use of the conjugate function. So, I effective conjugate is I effective e to power minus j phi, and hence P equal to real of V effective and I effective conjugate, and hence P equal to real power of V effective and I effective conjugate. An expression form for the complex power is S equal to V effective I effective e to power j theta minus phi. Well, the V effective I effective is the apparent power, and the angle of S theta minus phi is the power factor angle, that is the angle by which the voltage leads the current or may lag the current, and in rectangular form we write S equal to P plus j q, and where P is the average power and imaginary part of the complex power is symbolized Q, and it termed as a reactive power, and the unit of Q is defined in terms of volt ampere reactive abbreviated VR in short, and it is seen that Q equal to V effective I effective sin theta minus phi, where theta is the angle between voltage and current. So, P equal to V I cos theta, and reactive power is power that is periodically stored in a and returned to the circuit from energy stored element like inductor capacitor, that is volt ampere reactive VR, and that is Q equal to V I sin theta. So, apparent power, the magnitude of power that is apparently used in the circuit, that is volt ampere, that is P equal to V into I, and the typically the power factor, it is the factor the total power that is available for the consumption P f equal to cos theta equal to P upon V I, and reactive factor is the fraction of the total power circulate in the energy storing element sin theta, and these are the typically overview of power expression. So, we say average power is simply P and formula is V effective I effective cos theta minus phi, and we write a unit watt or write in short V or kilowatt or megawatt, and reactive power we represent by Q, which is the formula of it is V effective I effective sin theta minus phi, and the unit is volt ampere reactive or kilowatt volt ampere reactive or megawatt mega volt ampere reactive. And complex power we say S, which is typically P plus j q, or we say V I effective theta minus phi, and or we say V effective I effective conjugate, and this apparent power of course, we call it absolute value of this V effective I effective, and we of course, all them we call it volt ampere or kilovolt ampere or megavolt ampere MVA, KVA or VA. So, this is typically overview of power expression in total, and this is typically the kind of power in AC circuit. So, we call it instantaneous power PT, that is unit is watt, and we call it PT equal to VT IT, and it is the value of the power at a specific instant of time. It is not the product of voltage and current phasor, and average power is P, capital P we denote, and we write again watts, and it is in sinusoidal steady state it is V P equal to half V m I m cos theta minus phi, where theta is the angle of the voltage and phi is the angle of current, and the reactance do not contribute to P. The effective or RMS value is V RMS I RMS, and we call it V or A, and define it as I effective and root 1 upon T 0 to T I square dt, if I T is the sinusoidal, and then I effective equal to I m upon root 2, and apparent power value is absolute of S equal to V A, and absolute as V effective I effective, and if the maximum value of the average power can be P equal to S if only for pure resistive load, and power factor we denote by P f, and of course, we do not have a unit because it is ratio, and the ratio of average power to apparent power, the power factor is unity for pure resistive load and 0 for pure reactive load, and reactive power Q is the unit is VAR, a means of measuring the energy flow rate to and from reactive load, and complex power is S, of course, denoted in unit is VA, and conventional complex quantity that contains both average power and reactive power, and as we say P plus JQ. So, we call it like a power triangle, a load with the inductive component causes the current to lag the voltage, and if all the components are divided by I, we get the impedance triangle, and if we multiplied I, we get the power triangle. So, we have a here impedance angle, x axis R, y axis is X reactance, and the you can call it the their complex sum is typically the Z phasor sum is that, and if we multiply I, this become V R and then V X and totally the V, that is I Z, with of course, angle maintain all same in that, and of course, for power triangle if you multiply it further I with this, so it becomes a P equal to V I cos theta, then Q equal to I V I sin theta, and of course, S is your V I with again the your power factor angle, same angle theta in all the 3 diagrams like. So, we can say two of side of power triangle can be identified as active and reactive power, and hypotenuse has a magnitude apparent power. So, S is the complex power, and the source should be able to produce this quantity of complex power, and complex power captures all the information of power absorbed by the load, and the note is apparent power has the magnitude of V I and active power as V I cos phi, and if both V and I represented complex number. So, we say P equal to real part of V I conjugate and Q equal to imaginary part of V I conjugate, and you can say power triangle here P equal to V I cos theta, and the you can call it the typically tangent to is Q equal to V I sin theta, and then apparent power of course, is the phasor sum of this S equal to V I. So, we can say here if current I lags the applied voltage by phase angle phi as shown in the figure here, it can be resolved into two components OA typically in phase with the voltage, that is of this part of these two components, and OB in lagging the by 90 degree, and we can say power active power will be I V cos phi and V equal to O I into cos phi equal to V into O A watts, and therefore, O A is termed as the active component of current, that is in phase with the voltage, and the active component of current is I cos phi, and power due to component O B is V into OB cos 0, that is 0 90 0. So, OB is termed as a reactive component of current and reactive component of current is I sin phi, and we can say reactive power Q in VAR is VI sin phi, and the term VAR is the short for volt ampere reactive, and Q is equal to VI sin phi, and also P square plus Q square equal to VI cos phi square plus VI sin phi square, or you can take VI square out and cos square phi plus sin square phi becomes VI square equal to S square. So, you can say S square equal to P square plus Q square in this triangle. So, now coming to some of the numerical problem, a coil having a resistance of 6 ohm and inductance of 0.03 Henry is connected across the 50 volt 60 hertz supply. Calculate the current, the phase angle between current and applied voltage, the apparent power, the active power. So, the solution here with this phasor, of course, reactance of the circuit is 2 pi FL, that is 2 into 3.14 into 60 into 0.03 equal to comes 11.31 ohm, that is the reactance, and impedance will be under root 6 square plus 11.31 square, that comes 12.8 ohm, and current will be 50 by 12.8 3.9 ampere, and the tan phi is x upon r, that is your typically 11.3631 by 6, and it comes like 1.885, and from this phi is equal to 60 degree by 62 degree and 3 minute, and apparent power is S equal to 50 into 3.91, that comes 196 VA, and active power is apparent power into cos phi. So, it is a 195.5 into your 0.49469 equal to 92 watt. So, now coming to second example, a industrial consumer is operating 50 kilowatt 67.1 horsepower induction motor at a lagging power factor of 0.8. The source voltage 230 volt. In order to obtain the lower electrical rates, the consumer wishes to raise the power factor to 0.95. So, specify the suitable solution. So, although power factor might be raised by increasing the real power and maintaining the reactive power constant, this will not result in a lower bill, and it is not cure that interest to the consumer. So, a pure reactive load must be added to the system, and it is clear that it must be added in parallel. So, since the supply voltage of induction motor must not change, so circuit in figure is thus applicable. We interpret S1 and the induction motor complex power, and S2 as the complex power drawn by the corrective device typically in parallel to this. So, complex power supplied by the induction motor must have to real part of 50 kilowatt and angle of cos inverse 0.8 equal to 36.9 degree. So, we can say S1 equal to 50 at the angle of 36.9 degree divided by 0.8. So, this comes as a 50.J37.5 kVA. In order to achieve a power factor of 0.95, the total complex power must be S1 plus S2, that is 50 upon 0.95, that is at the angle cos inverse 0.95, that is 50 plus J 16.43 kVA. So, thus complex power drawn by the corrective circuit is the difference of the two reactive power, that comes S2 equal to minus J 21.07 kVA. So, the necessary load impedance Z2 must be found in several simple steps. So, we select a phase angle of 0 for the voltage source, and therefore, the current drawn by Z2 is I2 dash I2 conjugate is S2 upon V, that is minus J 21.21 21070 by 230, that is minus 91.6, or I2 equal to J 91.6 ampere. Therefore, Z2 is V2 I2, that is 230 upon J 91.6, that is minus J 2.51 ohm. So, coming to numerical example 3, an AC generator is supplying the load of 300 kilowatt at a power factor of 0.6 lagging. If the power factor is rated to unity, how much more power the kilowatt can generate the generator can supply for the same kilovolt ampere loading. So, since the power in kilowatt is number of kilovolt ampere into power factor, therefore, the number of kilovolt ampere is 300 by 0.6, that is 500 kVA. So, now when the power factor is rated to unity, number of kilowatt equal to number of kilovolt ampere, that is 500 kilowatt. So, hence the increased power supplied by the generator can be 500 minus 3, 200 kilowatt. Now, coming to an example 4, an inductor coil is connected in series with the pure resistor of 30 ohm across a 230 volt 50 hertz supply. The voltage measured across the coil is 180 volt, and the voltage measured across the resistance is 130 volt. well, calculate the power dissipated in the coil. So, complex diagram is constructed by first drawing the complex I, resistance voltage, complex V R, and then drawn with the phasor I. So, here it is like you have a voltage and you have a coil which have a resistance as well as inductance, and total voltage is your 230 volt, and here it is given that you have a typical volt. So, since neither the coil phase angle nor the circuit phase angle are known, so it is necessary to derive the remainder of the diagram by construction of the scale. So, circle of V, that is supply voltage, and VLR, that is the coil voltage, are drawn radially, radiating from the appropriate ends of VR, and the point of intersection of the circle satisfy the relation. So, we can here typically you have VR and you have VLR, and that is the V. So, you can say VR and you can have both the circle here. So, we have V equal to VR plus VLR. By the geometry we can say the diagram V2 equal to under root typically V square plus VLR square plus 2 VR VLR cos phi LR, and that we can say here 230 square equal to, just keep a square, equal to 130 square plus 180 square into plus 2 into 130 into 180 into cos phi LR. So, from here we can find out cos phi LR equal to 0.077 lag, and I equal to VR upon IR, that is 130 divided by 30, that is 4.33 ampere, and PR equal to VLR I cos phi LR, that is 180 into 4.33 into 0.077 equal to 60 watt, that the coil active power consumed by. So, now coming to the example 5, a single phase motor, AC motor operating of a 400 volt 50 hertz supply is developing 10 kilowatt with the efficiency of 84% and a power factor of 0.7 lagging. Then calculate the input apparent power, the active and reactive component of current, and their reactive power. So, the efficiency equal to output power in watt divided by input power. So, output power divided by V I into P F. So, it is a 0.84 divided by equal to 10 into 10,000, 10 into 1000 divided by V I into 0.7. So, V I equal to 17,000 VA, and input is now 17 kVA. So, current drawn by the motor input VAR divided by voltage. So, 17,000 VA divided by 400. So, that is 42.5 ampere, and therefore, the active component of current will be 43.5 into 0.7, that is 29.75 ampere, and since sin phi equal to under root 1 upon under root 1 minus cos square phi equal to 1 minus 0.7 square under root, that 0.714. So, therefore, reactive component of current will be 42.5 into 0.714, that is 30.4 ampere, and reactive power will be 400 into 30.35 divided by 1000, that is in kVR. So, 12.1 kVR. So, these are the some unsolved problem you can solve in the same line what we discussed other, and these are the references from where we have this material of this lecture, and thank you very much.